All right, so today we are going to talk about RSA Cryptosystem. RSA stands for the last names of the founders, Rivest, Shamir, and Adelman. But before talking about RSA, and in order to understand how this works, we have to talk a little bit about elementary number theory. So let's start with Euler's phi function. So let m be an integer, then the number of positive integers that are less than n and relatively prime to n is given by phi n. So by relatively prime to n, we mean that the greatest common divisor of n, and that number is 1. So Euler's phi function actually has the following property. Let n has prime decomposition n equals to pi to the power a1, p to the a2, and multiplied as such. So by prime decomposition, we mean that we write n in terms of multiples of prime numbers. Also, some of these prime numbers may have some powers. So then phi n actually means phi p1 to the a1 multiplied by phi p to the a2, and so on. So instead of now calculating this, you can independently calculate these ones and then multiply. That is the idea. And you might ask that, how am I going to calculate this one? So if p is prime, then phi p to the power k is just p to the k minus p to the k minus 1. Okay? So if k is 1, so if it is just a prime number, then this becomes p minus p to the power 0, which is 1. So it becomes p minus 1. So we know how to calculate the Euler phi function when p is prime. Also when p has a power on it. So whenever we want to calculate the numbers that are less than n and relatively prime to n, we first need to do the prime decomposition, then use this formula to calculate this. So in mathematics, we many times need this phi function, Euler phi function, because we need to know how many numbers there are less than n and relatively prime to n. Okay, we continue with some theorems from number theory. I'm not going to prove them, just take them as like a fact. So let p be an odd prime. Fermat's theorem says that a to the p minus 1 is equivalent to 1 modulo p. We are going to use it in the case when we want to check primality. So once we want to know if a number is prime or not, we are going to use the following theorem. So this is why these theorems are important. Euler's theorem is somewhat similar. This time, a to the p minus 1 divided by 2 is equivalent to ap modulo p, but this is Legendre symbol. So in order to understand what this number means, so this is not a simple division. We had to understand what the Legendre symbol is. So a and divided by p in Legendre symbol means that 0 if p divides a, 1 if a is a square in fp, and minus 1 otherwise. That is the definition. So this actually can only be 0, 1, or minus 1. The corollary is as follows: a to the phi n is equivalent to 1 modulo n. So in this scenario, n is in the above theorems, p was prime. Here, n doesn't have to be prime, but so this actually allows you to check the property. So this is a corollary from the above theorems. So just keep this in mind. We will talk about them when we want to check why RSA works and how we check the primality of numbers. Okay, so let's start with RSA in its basic form. So this is the main form. You cannot use it in practice, but in order to understand how things work, we have to talk about the basic form. First phase is key generation, then you can do encryption and decryption. So in the key generation phase, we start with randomly choose big primes p and q. Okay, so you should be able to somehow do that, and we will talk about how you can do that. But you can randomly choose big primes. Then compute p times q and say that it is n. So in practice, this n should be a very huge number. in terms of bits, it has to be 3072 bits. So this is why you should be able to choose very big primes. Then you choose a number E. This should be between 2 and n minus 1, and E should be relatively prime to phi n. Okay. So this is important, as you can. This is one of the reasons why I defined phi n in the previous slides. Recall that phi n actually equivalent to the multiplication of the primes, where you have the prime decomposition of n, but we already have prime decomposition of n, which is p times q. So in this case, phi n means phi p times phi q. But again, for the primes, it is easy to compute because phi p is p minus 1, phi q is q minus 1. So with this number, we actually mean p minus 1 times q minus 1. Okay, so this choosing E is just, it is not that actually important. And for ease of to have efficient computation, generally we choose a small e, sometimes like 3, sometimes like 2 to the power 16 plus 1, so that we have many zeros and only a few ones, so that the computations becomes easier. So this e is not that secret. And actually, it is not secret, but you don't have to be randomly choose it. But the secret part comes from here. You have to compute the inverse of this number e modulo phi n. Okay, and it might sound hard to do it because you have to find the number d, so that when you multiply d with e, you get 1 modulo phi n. But we have the extended Euclidean algorithm, which works really fast, and you can do this calculation in a very fast way. So once you do this, actually you are ready. Now the numbers n and e are your public keys. So you publicly announce it. N is generally referred as RSA modulus, and E is referred to as RSA exponent. But here the secret key, the private key, is D. Okay, only you know this. So you are not going to use P, Q, or phi n anymore, but they also has to be kept, so they have to be kept secret. Otherwise, we can break the system. So, as you can see, here the private key is D. So you might think that if somebody knows N and E, why cannot they capture D? Because knowing N and assuming that the factorization is hard, nobody will know P and Q if you don't announce them. So if they don't know P and Q, they don't know actually phi n, which is, P minus 1 times Q minus 1. So since they don't know it, they cannot also calculate this D. This is our assumption. So once you do this, encryption works as follows. When somebody wants to send you a message M, it has to be smaller than mod n, by the way. So in this way, in practice, you need to do some padding or dividing into blocks, but we are focusing on the basic form. So assume that somebody wants to send you a very simple message M and turns it into an integer. And once they want to send you the message, they calculate the eth power of this message, modulo n, obtain the ciphertext, and this is the message they send to you. So you want to decrypt it, but you do this as follows. You take the C, take the D power of it, only you know the D. Recall that D is the private key. And this turns out to be M modulo N. This comes from number theory, and I will show it in the following slides. But here, a few things we need to focus on. So here again, in the beginning, we focused on the hardness of the factorization problem. But here, when somebody captures C, it should also hard to, solve the somewhat discrete logarithm problem, because security also somewhat relies on it. All right. And more importantly, there are many GitHub repositories where they take E equals to 1 so that the calculations becomes really fast. But this definition where we say choose E larger than 2 is not just by, for convenience. It is important because if you choose E equals to 1, as many people do in GitHub, then encryption becomes calculating first power of M, which is also M. So a lot of people think that they are performing encryption, but they're actually talking in plain text due to GitHub repositories. Actually, this is the best way of introducing a backdoor. So, go to Stack Overflow, write a message saying that you don't understand RSA and ask if there is a easier implementation so that you can understand and use it. Then change your username, change your IP, and answer that email, that Stack Overflow message saying that you have a fantastic GitHub repository that you discovered years ago and it works fantastically. Give the link, and in that link you actually define E equals to 1 so that people think that they are going to use RSA, but actually they will be talking in plain text. This is actually this is the easiest way introducing, backdoors or viruses. And so, of course, don't do that. I'm trying to warn you about these cases. So, why the decryption works? Assume that we have to divide it into cases. So the message the person wants to send to you, assume that it is relatively prime to n. So because by chance they may choose P or Q, so it may not be relatively prime. So, but almost all the time they will be relatively prime like this. So m to the power ed actually means m to the power 1 plus k times phi n. Okay. And because this is how we chose D, right? Because it is the inverse of E, modulo phi n. So this means that it is equal to m times m to the power phi n to the power k. But recall our corollary. This has to be equal to 1 modulo n. So this is why 1 to the power k is 1. So you end up with m. Okay. This is why RSA works. So let's focus on the rarest case where the greatest common divisor of m and n is different than 1. So it can be p or q. So if p does not divide m, let's focus on this scenario. M to the power ed modulo p is equivalent to this one. You do the same trick, but instead of focusing on phi n, we are focusing on m to the power p minus 1. Okay, but again, recall that Fermat's theorem says that this should be 1 modulo p. So if p divides m, then m is equivalent to 0 modulo p, and m to the ed equals to 0 modulo p, and so on. So m to the power ed should be m modulo p. Okay. So in both cases, m to the power ed equals to m modulo p. Similarly, same proof applies for m to the power ed modulo q. So by Chinese remainder theorem, m to the power ed is equal to m modulo p times q, which is n in our scenario, right? All right, so this is why it works. I mean, I may give it in a very simple sentences, but the idea is that Fermat's theorem and the corollary allows us to have this decryption. All right, let's move on to parameter selection. We said that P and Q should be generated randomly, and they should be prime. In standards, a random number generator, which is a combination of physical random number generator and the deterministic random number generator, is used. If you randomly select an odd 512-bit number, it's prime with probability approximately 1 over 355. So you should be very lucky to randomly select a number, huge number, and expect it to be prime. So, of course, you shouldn't do that. Then a primality test should be applied to P and Q. This is the idea. You just randomly choose an odd integer, then perform primality test to check if they are prime or not. If they are not, you randomly select another one and another one, and until you find 2 numbers, P and Q, which you are convinced that they are prime, then you use them. So there's actually a polynomial time test for primality, which was discovered in 2002, Agrawal, Kagal, and Saxena algorithm. But the thing is that this is really slow in practice. Although it is polynomial time, the operations we perform, the algebraic operations, takes a lot of time. And when the numbers are increased, it is not practical to use this algorithm in practice, even if it is polynomial time. So instead of doing this, what people do is as follows. They use randomized polynomial time algorithms. Okay. Before talking about these algorithms, let's talk about some algorithm types, because Primality Test works like this. Most of the time, they are Monte Carlo algorithms. So a yes-bias Monte Carlo algorithm is a randomized algorithm for a decision problem for which the yes answer is definitely correct and the no answer is correct with a probability at most epsilon. So this kind of algorithms, when the output is yes, it is true. But when the output is no, it may be yes or no with some probability. This is the idea about Monte Carlo algorithms. There's also another type, Las Vegas algorithms. A Las Vegas algorithm to answer a decision or search problem is an algorithm whose answer is definitely correct if it finishes, because it may not finish at all. So you run the algorithm, you wait, but until you die, you don't hear anything from the algorithm again. So this is how the Las Vegas algorithms works. All right, so let's talk about now the Primality Tests, which are randomized. The basic one would be Fermat Test. So maybe to try to give the motivation, let's go back to RSA's first step. We say that randomly choose big primes P and Q. So we assume that we can check if a number is prime or not, right? Then we multiply both of them and obtain a number and say that now it is very hard to factorize it. So this looks like a paradox, because here we can actually check if these are primes in a fast way somehow, but we multiply them, the number becomes a little bit larger, but then we are saying that nobody can factorize it. So question is, if I cannot factorize it, then most probably I cannot factorize these numbers too. So if I cannot factorize them, how can I be sure that they are primes, right? So this is why we talk about decision and search problems. Here we are trying to solve the search problem by factorizing n, okay? And this is hard. Here we are trying to solve the decision problem, asking if this is prime or not. And answering this question is easier than the search problem. This is why we can use it in practice, okay? So we have fast randomized algorithms to check if these numbers are prime. But once we multiply them, the search algorithm to finding this factorization will be hard. This is the motivation, actually. So let's give an example where it is very easy and fast to check if a number is prime or not. But again, this is a randomized algorithm, and it is actually a Monte Carlo algorithm. So let me define it as follows. So recall that Fermat's theorem. So let's go back to Fermat's theorem. It says that when P is prime, a to the P minus 1 is equivalent to 1 modulo P. Okay, this is a theorem. This always works. So now let's go and see how we can use it in practice. So choose an odd n. This is what we choose. It is a large odd integer, and we want to check if it is prime or not. So what we do is as follows. We randomly choose a number a, an integer, and calculate the a minus 1th power of it modulo n, and check if it is equivalent to 1. Recall that if it is not, then this cannot be a prime number, because Fermat's theorem says that when n is prime, a to the n minus 1 is always equal to 1 modulo n. So if you randomly choose a number a, calculate the n minus 1st power of it, modulo n, and if it is different than 1, then you definitely say that this is a composite number. But if it is 1, it might be prime or not. This is why I call it a Monte Carlo algorithm, because when it says not prime, it is correct. But this time it says prime, but it is prime with probability something like 1/4, or maybe even smaller. So in order to modify it, we can use the Euler's theorem instead of Fermat's. Recall that in the Euler's theorem, idea was to check if a n minus 1 over 2, here there is a typo, this should be n modulo n, and recall that this is Legendre symbol. So if it works, then, if it doesn't work, then again we will say that this is a composite number. But if it is 1, then the algorithm will say it is prime, but this answer will be true with probability less than 1 over 2. Okay. So you can either use Fermat's theorem or Euler's theorem, or you can combine both and do some tricks. So this is called Miller-Rabin algorithm. The algorithm uses similar ideas. The answer composite is definitely correct, and the answer prime is false with a probability less than 1 over 2. Sorry, 1 over 4. So it is, I mean, a good gamble. So good thing is that you don't need to run this algorithm once and decide if it is prime or not, because 1 over 4 is still a huge probability. If it is not a prime number, and if you say that it's a prime number, then the whole system breaks. So this is why you have to be sure that it is prime. What you can do is as follows, go back to these algorithms. Since you choose a random A and check this, if it is 1, go and randomly choose another A and perform the operation again and again and again. So this is what you are going to do in Miller-Rabin. So if the test answers m times n is prime in succession, then the probability that n is composite is less than or equal to 1 over 4 to the power m. So if you increase m, this number will go to 0 when m goes to infinity. So for this reason, today currently we use m equals to 25, but if you want to be more certain, increase this number to 30 or something. So if the test is applied 25 times, and in all of the 25 times, if the algorithm says that it is prime, then it is prime with probability 1 minus 1 over 2 to the power 50, which is a very huge probability, something like 0.9999, it goes like that. But if you want to be more sure, just increase this to 30, then this would be 1 over 2 to the 60, which is a lot closer to 1. So this is what actually we use in practice. So all of the standards, like NIST standards, explain to you how to run these randomized algorithms. So the problem is that if you choose a number and assume that it is prime, but if it is not prime, then things go wrong. So if we go back to RSA, we said that choose two big primes, P and Q, and accidentally the number you choose, Q is not prime, and it is like multiplication of 2 primes, let's say. Then when you compute n, the decomposition of n actually becomes P times some even smaller numbers less than Q. So this becomes easier for us to factorize n. Okay, this is why you have to be sure that you are running these algorithms and checking that the numbers you chose are really prime numbers. And in practice, this sometimes fails. In practice, there are many RSA modulus which can be actually factorized because this prime selection process was not done correctly. So you have to be sure that they are really prime.